What would happen to Young's double-slit experiment if you put a barrier between the two slits, preventing interference? Welcome back to the Quantum Lab. I'm Joseph Stute. The question posed in the opening will be answered in a few moments. But first, let's take a look at a few Ripple Tank videos found on social media. The presenters proclaim photons act like water waves. No, I say they do not, and will present experimental evidence to prove my point. To help us keep track of when photons act like water waves, and when they do not during my demonstrations, I have created a Quantum Olympics scoreboard. Also coming up are a few tips for experimenters. This is my simplified Ripple Tank setup. Instead of springs, hooks, and a plug-in electric motor, I purchased a scrap piece of 1/2 inch PVC tubing at my local hardware store. This is the view below the Ripple Tank. The demonstration shows waves bending after passing through a single slit. There is no detectable interference pattern. Let's take a look at the result of a laser aimed at a single slit. Two surprising reflection patterns are created on the screen. You can watch the experiment that produced the two patterns by clicking here. Score 1 point for photons do not act like water waves. Change commonly accepted experimental parameters slightly, then keep testing. That's how I discovered two patterns from one slit. Back to my Ripple Tank. This time, instead of a single slit, I use an edge. Like the single slit demonstration, we see waves bend, but they never interfere. I will repeat the single edge experiment, only this time using a laser. I use two screens. A large fixed green screen and a movable white screen is used to unexpectedly twist the imagination. Here we see two patterns, created when a laser is aimed at one edge of the caliper I use in all my video demonstrations. To better see the patterns, let's go to lights out. The light-dark pattern on the left is easy to see. The one on the right is harder to see because the pattern spacing is so very small. I have found two ways for expanding small patterns. One, move the screen far away from the laser. When recently experimenting with a 2.5 millimeter diameter pin, the screen had to be placed 25 meters from the laser. Check this out. A simpler way is to place the screen almost parallel to the laser beam, like this. How my edge demonstration's laser dot turns into a light-dark pattern might be confusing. The laser dot is composed of light and dark spots we cannot see because they are small and close together. Twisting the screen spreads the light and dark spots, similar to spreading cards on a table. Score another point for photons do not act like water waves. Some patterns are best viewed with the screen at an angle or far from the laser. When waves flow past a ramp set at a slight angle, they only bend, never interfere. When the ramp's angle is increased, we see a wave interference pattern. I will do the same ramp experiment, only this time with a laser. Aiming a laser parallel to a polished stainless steel strip was the subject of my second video. By adding a slight ramp to the strip, we see reflected photons form a light-dark pattern. With a small twist of the strip, the pattern disappears. This setup shows photons act the exact opposite of water waves. Photons do not act like water waves. It's another point. Test something new. There are many surprises to discover. This is really getting monotonous. Obviously, photons do not act like water waves. I could not find one experiment where they did. Yet there are hundreds of people on social media that say photons act like water waves. As our friend Spock would say,
most illogical.
As you've seen, discrediting ripple tank experiments was relatively easy. I then turned my attention to Young's double-slit experiment, thought by many to be the heart of quantum physics. The mystery was how to prove the light-dark pattern created by the double-slit is not a wave interference pattern. To help you understand my solution, let's take a look at what the textbook said. This is a common diagram found in introductory physics textbooks. It is used to explain what is referred to as Young's interference pattern. When a photon approaches the barrier, it's supposed to separate into two, pass around the barrier, recombine, and self-interfere, creating a light-dark pattern on the screen. I have been unable to find an explanation of how a photon splits and later self-interferes. Some researchers call this mystery quantum weirdness. Here is my ripple tank double-slit setup. Note the red barrier's position between the two slits. Without the barrier, constructive and destructive interference is seen as expected. With the barrier in place, watch as interference is prevented. Waves bend only slightly, forming a continuous arc. This is an important difference to remember while watching my guardrail demonstration. I came up with the idea of placing a barrier, or guardrail as I like to call it, between the two slits. It prevents any possibility of wave interference between the two slits. After all my experimentation and inventing the Stute Guardrail, I began to think about the TV show Mythbusters. It's a program that tests urban legends, wild claims, and mysteries. How would the hosts go about debunking quantum wave theory? This is my way of showing them how to be Wavebusters. I call this setup Stute's Wavebuster Experiment. It is simple by design. The idea is for everyone to experience that aha moment when they see Young's double-slit experiment is interpreted wrong. Safety glasses. Think safety first. Laser. Guardrail assembly. A little more about that in a minute. This block will give the guardrail a little twist. And finally, a large piece of photographic paper. I invite you to join me and try this experiment for yourself. Instructions for assembling your own Stute Guardrail setup are presented at the video's conclusion. Now it is time for some wave busting. Step 1. Place the assembly with the tension pin 1 inch from the laser beam. The objective is to position the tension pin in the center of the beam, creating 2 equal parts with the guardrail in the shadow of the tension pin. The laser dot should look like this on your screen. Tape setup to the table. Step 2. Twist the screen until it is almost parallel with the laser beam. The screen should look like this. Step 3. This is where I lay the interpretation of Young's experiment to rest. Slowly give the guardrail a little twist. You will notice that some of the light spots on the screen start to disappear. Keep twisting until only one half of the light-dark pattern remains on the screen. Want to see that again? Here it is on the Quantum Lab scoreboard. Look at the guardrail. You will see the screen's missing light spots. The guardrail prevents photons traveling around the left side of the tension pin from interfering with photons traveling around the right side. The guardrail makes constructive and destructive interference impossible. Young introduced his double-slit experiment over 200 years ago. Apparently, no one has asked the critically important question, what would happen when a barrier is placed between the two slits, preventing interference? The answer is absolutely nothing. Looking closer at our Quantum Lab comparison, photons traveling around the right side of my guardrail barrier create one half of the usual light-dark pattern on the screen. Photons traveling around the left side make the pattern's other half on the guardrail's twisted end. This shows constructive and destructive interference is impossible, yet the light-dark pattern is still there. Score! Game over! Water waves did not get a single point. Beware of easy, commonly accepted explanations. Research often stops before key concepts are fully tested. Back daydreaming in front of my favorite sheet of graph paper, I started to wonder how the world of physics, famous for mathematical exactness, could accept a concept like quantum weirdness. I started to laugh when I remembered an old cartoon and immediately sketched my new update. My simple guardrail experiment has far-reaching implications. It provides more than adequate proof that the light-dark pattern in Young's experiment is not an interference pattern. That myth is busted. I think sufficient evidence has been presented to safely say photons do not act like water waves. And the light-dark pattern in Young's double-slit experiment is not proof of wave interference. If we're ever going to understand photons, we have to stop thinking of them like water waves. What do you think? Please comment below. As for me, anybody want to buy a used ripple tank? Want to show your friends you do not follow the herd? Check out my t-shirts in the Quantum Lab store. Also available are other items with my retro cool Quantum Lab logo. Share with everyone that you like new twists to old theories. As promised, here are my Stute Guardrail setup assembly instructions, starting with the supply list. Safety glasses, laser with a beam about 3 millimeters in diameter works best. One piece glossy photo paper, 25 millimeters by 50 millimeters. One piece 100 by 200. One piece aluminum foil, 25 by 48. one tension pin, 1.5 millimeters by 25 millimeters, from your local hardware store, binder clip, glue stick, one piece of cardboard, 125 millimeters by 250 millimeters for the base, adhesive tape. Now that we've collected all of our supplies, let's assemble what I call a guardrail in 3 easy steps. Apply a thin layer of glue to the matte side of the photo paper. Press the aluminum foil onto the glued surface even at one end, and leave a strip of exposed photo paper at the other end. Smooth out any bumps or ripples. Slide the guardrail into the tension pin slot. It is easier to slip the end with the exposed photo paper. The aluminum foil can get in the way. This combination is the guardrail. Next, place the assembly into the binder clip. Make sure the guardrail is perpendicular to the base of the clip. Finally, tape the binder clip to the cardboard base. And we'll have to build that movable screen. Glue the 100 by 200 millimeter photo paper onto a piece of cardboard. Next, cut a piece of cardboard 50 by 150 for what I call a kickstand. Bend the cardboard in half and glue one portion to the screen's backside. There you have it, a standing movable screen. Give it a twist, and it will turn a laser dot into an elongated light-dark pattern. Have fun experimenting, and I look forward to hearing about your results.